All right, so I will get going. I hope you're all staying safe and all the pleasantries, and we don't get too fast in our seatbelts much these days. So this will be an opportunity to do that. Do I share my video too, or no? Or does it matter?
No, you're sharing your screen right now with your slides is perfectly fine.
Very good. All right. So as Brian mentioned, we're going to talk about the top 5 technologies that we think all organizations must understand. And we'll go through it in relatively brisk fashion. Those of you who listened to me, I think it was a few years ago when I spoke at the actual physical conference at Stanford, I did talk about the revolution that was happening. And revolutions change things. Fundamentally, our thesis is that as humanity, we have gone through agricultural revolution and then industrial revolution and now information revolution. And each of these revolutions have sub-revolutions, but I decidedly do not like fourth industrial revolution. It makes it sound like the 9th agricultural revolution. And I think we are very much in the middle of an information revolution. And just like industrial revolution changed most aspects of life, the information revolution is just starting and it will be just as pervasive. And this is really not a bad time for those of you who are inclined to go and read the history of what happened in the late 1700s, 1800s, early 1900s. You know, within kind of that 50-year, 100-year period when it was happening, mostly in Europe, a little bit in the US, and then a lot more in the US. And if you look at the history of art and history of literature and history of technology and factories and religion, you could very much come away thinking that we've seen this movie before, and society is responding to this massive change in ways that are in fact quite similar in many ways in what happened before. This is also why we are seeing so many big trends at the same time. I usually joke that there are not enough CTOs, even in a big company, to put your arms around all of these different technologies and trends that are there. So it really is too many buzzwords. On the other hand, understanding them in one place is something that we believe is mandatory. So fundamentally, we think the critical technologies and what the future looks like is that we have kind of going from the bottom to top is that you have IoT as the fountain of data. 5G is how it's going to get communicated. AI and HPC is how we make sense of that data. Blockchain is a new way of transacting the data. And things like quantum computing and similar technologies are how we're going to accelerate some of the harder problems that we need to solve. All of this, plus all the digitization that we have done already over the past couple of decades, have created what we call enterprise as a system. The enterprise, the organization, whether it's academic or government or commercial, that organization is increasingly acting as an organism. It's acting as a system, and it is connected to outside of it also as a system. And all of these technologies, sometimes they are relevant to exactly what you're doing. Sometimes they're not exactly relevant, but then you wouldn't know it until you studied it. Fundamentally, they are an opportunity and a threat. If you do it and you do it right and you do it timely way, you're probably good for the next couple of decades. If you don't, you might be okay if it doesn't really impact you, but if it does, that really can spell trouble. So as a result, we see organizations kind of hurrying up, trying to figure this out, really not even knowing whether or not it really impacts them. But it's kind of what they have to do. A lot of this is about what? It's about data. It's about digitization because that's what information revolution is all about. And you need good data. You need the ability to interpret the data, and you need to set good policy based on the data, plus your human values, plus everything that makes the totality of our policies good. You know, I look at this slide, and that is almost exactly what we're going through right now with all this virus thing. We don't have good data. Our ability to interpret the data is all over the map, whether it's literacy or numeracy. And as a result, the policies that are being set don't seem to be necessarily informed by everything that we could bring to bear for it. So hopefully next time we'll be more prepared, but that's kind of the reality right now. I'm going to jump right into IoT, and this slide you may have seen from a couple of years ago because I've been carrying this one for a while. Every time there's a new source of data, a giant industry appears. And sources of data have gone from organizations where we had MIS to people when we have social media, and they've gone from systems to now things. The whole point is that you extract information content from these sources of data, you structuralize the data, and then you can run apps and make sense of it and turn it into value. So IoT really is about everything is smart. It is very difficult to do because it requires you to know how to do embedded programming, mobile programming, cloud programming, embedded infrastructure, mobile, cloud, and those are three very different disciplines. It is really difficult to find developers who really understand all three, so you really have to have a roof underneath they can all collaborate and figure this out and build a system. On top of that, you need to have scale, reliability, speed, ease of use. The environmentals are a big issue. If you look at a connected light bulb, the temperature in that light bulb can get up to really pretty high levels, right? 125 degrees or so even for an LED. And that can really have an impact on what sort of semiconductors you can put in there or not, and what sort of reliability you can expect. And then you're going to have to sell it for like 10 bucks. So then all the stuff that you added, and then you get the margin out of it. You know, if you buy it at 10 bucks at Home Depot, it probably costs them $3 or something. So how much can you stuff into that little thing before it's actually smart and butters your toast? It's like really difficult to do. And of course, anything that has an IP address or anything that is connectable through any network is also an attack surface. So we see a massive attack surface actually being built right now that is just, makes the bad guys happy. And then there are lots of protocols from low power wide area networks, Zigbee, Sigfox, LoRa, all the way up to what we now look at with 3G, 4G, 5G, which I'm going to look at, Bluetooth, low energy, Wi-Fi, and then some of the serverization and virtualized network functions that are coming like Open RAN. And then this picture underneath, really you want to go from left-hand side up and then come back down through the right-hand side where you go from machine to machine, and then you have events and data that triggers something as it goes up to the cloud, and then you match it with your business objectives, and then you control it back. So the point here is that IoT isn't just a one way from the device to the cloud. You also need to come back from the cloud to the device. And we have a better picture of this here. So IoT, because it's a fountain of fountain of data, everybody talks about it as data is the new oil. So you really are fundamentally talking about atoms that are things, and those are the things that are smart and they're connected, and then bits that are the information that they spew out. And then you have a concept of a digital twin. You also have a concept of a physical twin. And that's really the dance that is going on that is going to be building what we refer to as the data economy. So the data economy really is what puts the transformation into digital transformation. So when you do digitally transform your business, you really are going after the data economy. If you're not there, maybe it wasn't quite as transformative. But when it is, it truly is transformative. And then the picture on the bottom is what I was just saying earlier, that you've got data sources that are the devices that creates data supply. The data supply turns into a data product, and the data product leads to a data market. So now you are beginning to see the supply chain of data. Just like a physical supply chain, you now have a digital supply chain. Just like the physical supply chain has a workflow, the digital supply chain has a data flow. And you want to have device and mobile devices. Invariably, there's a mobile app that goes with these connected devices. So you've got the device and mobile to cloud, and then cloud to three things: to insight, to control, to commerce, to governance, which you could kind of put under those three umbrellas. And then you've got security that cuts across the whole thing. 5G. 5G, of course, is a big hot potato right now. It's a matter of geopolitical importance these days. What that's about is that everything is connected. 5G is an incredibly large promise. Bandwidth can go up to 20 gigabits per second. Latency down to 1 millisecond. Now, all of these are lower bounds, by the way, and upper bounds. Like 20 gigabits per second is probably the peak guaranteed not to exceed performance. 1 millisecond is the lower bound. Precision, less than 1 meter, without actually triaging and trying to do predictive location, position, precision, and accuracy. but less than 1 meter is a very, very ambitious thing. Density, you can have more than I think the spec says that you need to support 1 million devices per square kilometer. A very big part of 5G is the back end. The back end is significantly easier and more modern than the 4G, 3G, LTE back end for the telcos. And you really want that to give you the flexibility and lower cost, etc. Low power, something like 90% less. And of course, 100% coverage. And of course, when you're trying to connect things to the net, you want coverage, you want power, you want all of the above. So the promise is huge. Some of the buzzwords we want to learn about this is eMMB for Enhanced Mobile Broadband, and that's actually the frequency range that is available to it, 30 gigahertz to 300 gigahertz, the millimeter waves, URLLC, ultra reliable low latency communication. That's where you get the 1 milliseconds. MMTC, massive machine type communication. That's the part that's really focused on IoT and how all of these things are going to be connected well. And also, when you think about all the geopolitical parts of it, remember that there are certain classes of technologies that need to be in place. You need handset. For example, Qualcomm has very good handset chip for 5G, but they don't have the back end. They don't have the switches. You have tower that you need to put something in tower. So now you have to go source who does what across the world that can provide a full solution, and that causes some of the discussion that we hear in public. There's also a new strategy, and that's called Open RAN, and that's for network function virtualization. Facebook has a project called Open Cellular. You have to remember that folks like Facebook and Google are very much into every part of every technology, and they want to have it play. And then the use cases that look real to us are telesurgery, to the extent that that's real, but certainly nowadays it would be something that people may actually want if it's reliable. Driverless cars, and that leads to two other buzzwords. One is vehicle to everything, V2X, but also vehicle to vehicle and vehicle to infrastructure. And of course, edge computing, something that is actually near and dear to our HPC hearts. So that leads to supercomputing. This actually is a new slide compared to the one that I've been using for the past 25 years. But the point of supercomputing is that everything is computable. You have digitization, you have data, you add science, you add IT services, you add modeling, and now you've got HPC. What has kind of thrown a monkey wrench in this thing is AI. And those of you who listen to Radio Free HPC know that we just had a discussion about when AI is real and when AI is not real. And are you doing it just to get funded because it's kind of the thing to do, or do you actually have a legitimate use case for AI? And we've kind of identified a few that look quite real. But again, the story here, as always, that you have a new idea, you generate new data, you come up with a new model, and you show a new way to solve something or to predict something. And on the right-hand side, you've got the various modes of computation, from communication, which is so critical, to automation, to visualization, and to instrumentation that gives you new data. So when you draw the lines between all of these, this becomes a little bit more of a spaghetti than it used to be, so I just removed the lines. Parallelism. We want things to go fast, and we do that by replicating things. So if you look at the y-axis here, in terms of compute bound to memory bound, and that is a measure of the compute intensity or the data intensity of the application. On the lower x-axis, you've got concurrency, serial on the left, parallel on the right. You've got these traditional models that you want to accelerate. You've got AI that you need to accelerate. And you've got algorithmic strategies to speed up things by taking a generalized algorithm and shrinking it to the specific use case to make it go faster. That is also quite common. So all of that requires you to go faster. How do you do that? You replicate cores and you get vector processing or GPU. You replicate the entire system and you get clusters, or you replicate memory pipes and you get into in-memory and non-touring machines and things like that. Now take this picture and imagine that to be the upper left quad of a 2x2. And that's what you see in this slide. So that corner on the top is the previous slide. And that, let me map to the slide first. So on the x-axis here, you kind of have digital on the left-hand side and analog on the right-hand side. On the bottom, you've got quantum physics. On the top, you've got classical physics. Everything we've been doing is really on the upper left-hand side. And what's going on in that upper left-hand side is that we live in a world where we are post all the laws that really govern what we did. We are post Moore's law, we are post Dennard scaling, we're post all these other laws that exist. The bottom-hand side of it is all quantum computing. On the left is quantum gate, which is digital quantum. On the right, you've got quantum annealing, which is analog quantum. And on the upper right-hand side is mixed signal. And that's actually, this slide is a collaboration with a company out of Stanford called Radical Semiconductor that Steve Jones put me in touch with back at SC19. And I've been working with them and just having a great time watching what these guys are doing. But they are working on mixed signal, and that's actually using analog computing to accelerate some things. And for things like hypersonics or even some of the future AI applications, you can see a scenario where if you get the analog computing right, and it's not easy to do, but it can be done, that can really accelerate things and get you to the 5-yard touchdown. The apps and containers, you have seen this slide perhaps before, but if you take an application, there is kind of the logic part of it, the control part of it, and the data traffic part of it, the intra-application communication, not the inter-application communication. Now, intra-application communication is very familiar to HPC because that's what MPI essentially is. That's why you've got the offload engines. That's why you've got the speed that you can get from modern switches, et cetera. You fast forward from left to right, you just basically see more of everything. That the topology and the network services and the security of the application itself are now issues. The elasticity, microservices, all of that within the control logic part of it is an issue. The SLAs, et cetera, et cetera. And then you look at IT transformation to cloud, the promise, the reality, and the solution. Thomas and Mohan just presented a very elegant solution. And what you see here is along those lines. Is that the promise is that you have an application, you move it to the cloud, and you're done. The reality is that, no, you're not done. You kind of end up having to go to multiple clouds because that's what you want to do. And then you need to have application performance management, cloud management platform, software-defined networking, application delivery controller. And to bring all of that together in a solution, it is becoming a big enough problem that you really do need to form companies to go solve it. So as you know, if you've been tracking what I have been saying, I believe the part of AI that is interesting and it works is HPC. And without HPC, it was languishing for the previous 50 years. So to me, AI is really high-performance AI. On the other hand, it's got its label because as an HPC community, we like to let other people kind of steal the show and run with it. And AI has done that too. So it is what it is. But you kind of have IoT, which is the fountain of data. You look at the big rules of big data. I have an article on this. There's something like a dozen rules that you really want to pay attention to. Again, some of them are extremely relevant to what we are doing today with this whole virus thing. And then the bottom portion just shows that as you have the big data on the bottom, cloud in the middle, and AI on the top, you really are having a numerical approach to it and a logical approach to it. And ultimately, you need to combine the two to have the proper AI that is going to guide you. The grand challenges of AI are the unpredictability of the consequences. The problem with AI is that it only works in the very, very, very precise scope for which it is defined. And the moment you step outside of that scope, you're on your own. If it works, you're lucky. And invariably, you do step out of it because it is impossible to predict it in advance how these things are going to be used because it's just impossible to look at all the possibilities. So that's the system complexity can exceed human competence. There's an ethical complexity. Is it good used for good or evil? You can't even set that ethical complexity and avoiding a Darwinian mistake if you don't have a legal framework that guides you. And you can't have that without the ethics. So it's good to see that there are centers opening around the country that around the world that are doing that. We kind of like the Asimov rules for robots that should be in place. And then we talk about autonomy. And again, as I said, autonomy is limited to the precise definition of the scope. And then that also leads to our tolerance for mistakes when something doesn't go right. Quantum computing. Quantum computing is about everything is a probability function. It just turns out that we can control these probability functions and harness them to do what we need them to do. Somebody put it really well. It is overhyped and underestimated at the same time. It is very hot. A lot of progress is made. A lot more progress needs to be made. The current state of the market is what they call noisy intermediate scale quantum computing. And that's basically because we're past a couple of few qubits, but we're not to the level that we really need to, and they are too noisy. There's a global push. There are literally tens, if not hundreds, of serious efforts in multiple geographies for multiple applications, etc. It's fundamentally used as an accelerator to classical computing. The programmability of them is advancing. It's all on the cloud. Every quantum computing vendor and some of the software vendors have their development environments online. You can join it for free. Some of them even throw in a little bit of compute time to entice you. So if you have any interest at all, kind of learning it is not that hard these days. And then there are several approaches to get to quantum computing from silicon-based or boson sampling, so photonics to positronics or trapped atom, trapped ion. And it's really just hard to tell which one of them is going to do the right thing or for what application. So also, as of about a couple of months ago, we formally divide the quantum computing market into three segments: quantum computing, quantum communications, and quantum sensing. Quantum computing is about quantum annealing and then the gate model. Cryogenics are usually required. Decoherence and quantum error correction are really big issues. And there's a metric that's emerged that IBM put forward that is just making sense. So other people are starting to adopt it. And that's a notion of a quantum volume that looks at how many qubits you've got, how well connected they are, and what's the fidelity of them. Quantum communication is happening. It is basically entangled photons. It is already in use in parts of Wall Street and parts of financial services. You can actually go buy services that do quantum key distribution, and they can do that like across the river from New York to New Jersey or from Shanghai to like Vienna. Those are the two examples that keep popping up. They also are looking at teleportation. So one can see a day when you actually are transmitting data through quantum. But you have to remember that whereas in data communication, you can copy the data, with quantum communication, you cannot copy the data. But you can, in fact, swap states between a qubit and another qubit. So that's kind of how they push it forward in a ripple sort of a way. And then for quantum sensing, the one bullet you really need to know is that second one, and the second bullet is that we're getting to single atom level sensing. The whole idea of quantum sensing is that if you perturb the quantum state, you can measure in a more accurate way. And it's already been used for atomic clocks and things like that. Now we run to digital money. If you are interested at all into blockchain and cryptocurrencies, the best place to go is the original so-called Satoshi paper that was launched in October 2008, allegedly because we had another economic meltdown back then. But do Google Satoshi paper and it just shows up. And it is extremely accessible. It's really easy to read. It's not a very long paper. And it just tells you everything you need to know. And you probably know more about most people if you just read that. The components of cryptocurrencies and blockchain are coins and tokens, virtual addresses, cryptographic addresses, wallets, smart contracts. Smart contracts are very, very important. Exchanges, these are kind of exchanges of value, and then the applications that govern these things. And Bitcoin continues to be basically digitized gold. If you think of it as digitized gold, it's quite easy to use. It's quite available. You can go to Fidelity and get it, or to Coinbase and get it. And then the whole thing is getting just increasingly accepted. There are increasingly good use cases, but there are legal challenges and there are technical challenges. I will skip on this, but if you get the slides, you can read it. This is really what is digital money. I'll do maybe the middle part and then not the right-hand side. So money wants to be store of value, and that leads to how safe is it? It's a unit of account that leads to what is the money supply, how is that regulated? It's a medium of exchange. That means it needs to be stable and not so volatile. And of course, right now we see volatility on every commodity out there. Just look at the price of oil. So it's really, the whole thing is really in shift right now. And it is causing everybody to really revisit what money is and what money will be. We actually have an entire talk on the future of money. If you're interested, let me know. We'll do a private screening for you. I will skip the private public key encryption concept, but Basically, you have symmetric old days, asymmetric the new ways, and then there's also a quantum way of doing cryptography and quantum safe cryptography that tries to avoid exposure to quantum computing, being able to crack the code sometime in the future. It turns out that having provably random numbers is really interesting, and that's the one application where we've got quantum supremacy. This slide shows how a software stack is starting to emerge for blockchain and quantum computing. I'll just cover the top part of it, is that if you are dealing with something that's naturally scaled, that talks about things that are naturally distributed, that you can get participation from the members of that network, then you're probably eligible to use blockchain. If on top of that, you need traceability, you need smart contracts, kind of program trading, in other words, and if you need to manage rights and authorizations, then that adds to your case. Otherwise, doing it the way you did before is just fine and preferable and cheaper. Smart contracts are essentially code, just like Thomas was saying, infrastructure as code. Everything is code, and these smart contracts are essentially languages, and you write programs. What is interesting to see is that when we devise a programming language, we want it to be Turing complete. We want it to be able to do everything. It turns out that's not quite a really good thing, because then you can't verify it. So in fact, smart contracts that are more like a finite automaton or a discrete engine are better. And this is my last slide, which is when things change, they're not the same anymore. You've seen me do this because this is one of my favorite quotes, and it's not even mine. And I thank you. Was that fast enough?
Yeah, that was perfect. We do have one question for you, Shahin.
All right.
And that is, when do you expect quantum computing to really become a player in the computer industry?
Oh, I think, as we said before, the horizon is pretty far out there right now. What we are, however, seeing is that quantum computing is leading to quantum-inspired algorithms. They call it dequantization in the trade. Is that you try to solve a problem in a quantum way, you come up with a brilliant algorithm that does it in quantum computing, and then you say, hang on a second, I can implement that on my cluster with GPUs. And then you do that, and then, oh my God, it's like 3 times faster than what you were doing before. So you end up not using a quantum system, but going through the process gave you a newer algorithm. So we see a few of those. I expect that in 2020, we'll see a couple of other things that achieve quantum supremacy, but generally it's a few years out. It's like debugging. It's not done until it's done.
Got it. Okay, fantastic. Well, thank you, Shahin. I really appreciate it.
All right. Thank you all.